Good afternoon.
Good afternoon. I will chair this session.
Thank you.
Okay, thank you very much. Actually, I'm maybe out of this, the research field, but I'll try. Okay. Oh, Dr. Shawan. Oh, I was. Hi. I will chair this session.
Thank you.
Oh, maybe I'm out of this, field, so I will try, but
I'm also a beginner.
Oh, don't say that. Okay, so I have 2 minutes to go, right?
Should I try to share my screen now? Just
Please.
test whether it works.
Yeah.
Okay. Let me see how it works. Okay, strange. Oh. Because I have 2 screens, so I need to.
Oh, yeah, I know. Sometimes confusing.
Yes. Okay. I'm sharing my screen.
Yeah, it's coming. Okay.
Do you see my?
Yeah, I can see your slide, but not the presentation mode.
Yeah, that's it. If now I'm in the presentation mode.
Oh, that I can see your the not the presentation, but just swap the
Yes. How
display.
about now? Is it
Yeah,
presentation mode?
that's good. Yeah, that's good.
Okay, good.
Okay, so
I
please
have two
leave it.
screens, so I need to place it.
Okay, yeah. So please leave it. We only
have
have about
2 more
1
minutes.
Yeah, 2 more minutes. Yeah.
So I have 40 minutes, right?
Yes, 30 minutes for presentation and 10 minutes to discussion.
Okay.
Okay.
My talk may end a bit earlier.
That's better.
Yeah.
Professor Horio, the third speaker today will be Professor Wei Chao Yu from Fudan University. The third speaker. Yeah, there is a
Third speaker
change.
changed.
Okay.
Okay. I didn't get the name, but Fudan University. Okay.
From Fudan University.
What? Please give me a name again.
Professor Yu.
You. Okay.
Yeah.
Okay. Title is the same.
Title is different.
Oh, different. Okay.
Actually,
All
I
right.
have sent. I just. 15 minutes ago, I sent an email.
Oh,
Maybe
really?
you can. Yeah, you can check it. Yeah.
Okay, I will check this. Yeah. Okay, let's see. Yeah, thank you. Thank you. I got it. Okay, so everyone, good afternoon. I'd like to start session H, and we have 3 speakers. The first speaker is Professor Wang Xiao from NTU Singapore. Could you start your talk if you're ready?
Okay. Sure. Great. Thank you very much for the invitation and also introduction. My name is Wang Xiao. In scientific publications, I go by my pen name, which is Renshou. This afternoon, I'm going to discuss nanoengineering or spin texture for multi-state applications. First, I have to admit that I'm the beginner. I'm the beginner in the field. I'm just mainly trying to learn. So, and also the study would be a bit towards fundamental research. And I hope probably I can learn more than present more. First, I'm going to give introduction following the pattern that first a few minutes, I'm going to discuss some basic concepts or basic motivations. I'm sure, so we all know that we are living in a binary world. That means in terms of the computation and data storage, we all go by 1 or 0, especially in the phone and the computers. So we are very familiar with it and we are making use of it. However, in order to, if we envision future, especially because Moore's law will sooner or later, or not very soon, sometimes later will be broken. So we have to envision some new structures, new ideas. So one possible ideas is try to have a multi-state storage within the same unit. If we talk about data storage by magnetic structures or using magnetic properties, we of course typically have spin up and spin down, try to store it. And in principle, we can have this like tilted or non-perpendicular magnetizations for data storage. However, generally they are not very stable or they're not volatile, meaning that if we fall back to the ground state, that we will go back to this perpendicular structures. So our plan is probably we can try to build a multi-layer structures and utilizing, for example, the antiferromagnetic force or antiferromagnetic coupling to play with the bottom layer. So maybe we can have a multi-level structure for multi-bit storage or multi-state applications. This is actually not something new or not something only from us. This is kind of the well-known structure. But anyway, so applying these ideas, so we can have these multiple states within the small cell. And the issue, of course, is how do we distinguish these states? How do we realize for example, the reading of these states? Because if we write them, we also need to read them. Talking about the background, or like talking about the basic concepts, if we talk about the spin textures, generally, if you talk about the microscopic structures, we mainly see this as magnetizations. Basically, we talk about whether the material is magnetic or not magnetic. However, if you zoom in down to a very small range, like even probably atomic range, so we can see how the spin arranged. And this is the spins arrangement. We can call them like spin textures. Of course, there are different types of spin texture. There are ferromagnetic spin texture, means all are aligned in one direction. There are also antiferromagnetic spin texture, means they are aligned anti-parallelly, or there are different types of antiferromagnetic spin textures that can be up and down or this. Of course, there could also be canted ferromagnetic spin textures. It's colorful, so this means it's probably allowing us to play with the textures. From theoretical point of view, these colorful or rich spin textures are governed by a lot of interactions. For example, there's a spin exchange interaction. They are also determined of the easy access. There are also external magnetic field. So all those spin textures gives us different magnetic states and also different spin textures. I think roughly in the past 10 years or close to 10 years, skyrmion, which is a very appealing magnetic particles, attracts a lot of information, attract a lot of attentions. So people study the skyrmions, they build a different structure to host skyrmion, and they manipulate skyrmion. Also, some of the very promising applications can be utilized in real applications. Based on my limited understanding, so a lot of people, they work on skyrmions, and some people, or a portion of the research community, also working on skyrmion bubbles, which is not absolute skyrmions. So in this talk that I'm going to present today, we are more towards the skyrmion bubble or skyrmion-like nanomagnetic structures. Of course, we would like to have the ideal skyrmions, but so far, either it's very difficult or we don't have the ability to create an ideal skyrmion yet. Of course, skyrmion bubble is also interesting, and it's also stable, and we can probably to squeeze it and also play with it. This guy gives us flexibility to create multi-state or different different states of the skyrmions. And talk about the skyrmions, or now I'm going to talk about these skyrmion-like domains. There are generally two types. One is itinerant, and the other is localized. Itinerant means this skyrmion or skyrmion-like feature. They can move, the mobile. They can play with. They can push the skyrmion from one position to another position to create some appealing phenomena. And also we can have this localized skyrmion that the states are there. In the study or in the small work that I'm going to discuss today, we mainly use the localized skyrmion-like magnetic domains. So basically we force them stay in one place, and we just squeeze this size and also play with its spin polarization or spin states. But both are interesting, and you can see there are for both types of skyrmions, there are a lot of studies and there are a lot of appealing properties. Skyrmions as a very interesting particles, they have a lot of applications. For example, they've been used in reservoir computing. They've been used, there are skirming-based synapse arrays that can be used for neuromorphic computing or brain-inspired applications. For example, in the Nature Electronics paper published last year, so they build a synapse, so based on the skirming structures, so they can build array and even devices. Of course, in our device, in our study today, we also think about how to electronically read the signal. So basically, that means we cannot, let's say, read the device using an optical microscope, then try to read this and remember by our brain, right? We have to convert it into electrical signal, either a current or voltage. And we study the electrical property of our skirming-based structures. So now I'm going to discuss some of our experimental results. In our study, of course, as I said, we deal with the localized skirming-based structures or skirming-like structures. So we build a multi-level or multi-layer structures. For the antiferromagnetic coupling, we use ruthenate. We play with the thickness of the ruthenate to get the ideal antiferromagnetic coupling. And for the perpendicular magnetic anisotropy, out-of-plane magnetization, we use the cobalt platinum multi-layers. We can play with the repetition of the layer. In the structure on the left side here, let me change to a pointer here. On the left side here, so this is our zoom in microscopic structure of the device. So on the below, we have repeated cobalt platinum structure. Then in between, there's a ruthenium antiferromagnetic spacer. On top of that, that's also a PMA, perpendicular magnetic cobalt platinum. On top, there's also a titanium, because that's layer can protect the sample from oxidation. Basically, it's a protection layer. So when we grow these multi-layers using a sputtering, and then we etch first the top multi-layers into a nanodot, of course, patterned by E-beam lithography. Then for the bottom layer, we also use the etching, and then we contact with the electrode. So eventually we have electrical contact on the sample. In the structure, we are able to play with several parameters. For example, especially for example, the N, which is the number of repeat here. We can play with the N. We can also play with the D, which is the diameter of the upper nanodot or nanodisk. We can also play with the Q. Q basically means Q basically means we can play with how many nanodots or nanodisks on top we would like to have. Of course, we can also play with S, which is space between the nanodots. And you can see on top, this is the optical image of our whole bar device. The whole bar device, we can do the wire bonding, we contact the electrodes. So then because of electrodes and the wire bonding, we can read the electrical signal. And next, we are dealing with this skirming-alike or skirming-like magnetic features. So that's why we have to make sure that it is indeed at least close to a skirming. So we did a simulation on if it is a skirming, how the magnetization will look like and how it will reflect in a magnetic force microscopy image. On the right side, that's the simulation result. On the left side, that's experimental result. As you can see that based on the experimental result, that simulation, that we can have a skirming-like magnetic structure. That's we have. Okay, as we said that we can play with the diameter of the nanodisk, space between the nanodisk, the repeating of the bottom layer, and also the number of the nanodisks. So we have those samples, and we already proved that there is skirming-like magnetic features. then the next step we need to do is characterize its magnetic properties. To characterize the magnetic properties, we first use a MOC, which is optical technique, to study the magnetic features. And you can see that when we sweep the magnetic field, for example, from a positive 5 KOE to negative 5 KOE, or slightly larger, I can already see that there are multiple features. Right? There are different features when we sweep appears when we sweep the magnetic field. Let's talk about n equals to 2, which means the bottom layer repeats 2 times, and d, which is d equals to 600 nanometer. That means diameter is 600 nanometer. And you can see from the one ground state can slowly convert into an antiferromagnetic state to a skirming-like texture or skirming-like state, and eventually to a ferromagnetic state. If we talk about we change the n repetition of the bottom layer, we can have a similar things. The skirming state is slightly smaller. Right? You can see there's an antiferromagnetic state, there's another antiferromagnetic state, and skirming state. So basically, by playing with the n, we can play with the window of the different magnetic states. Of course, those states were also characterized by the magnetic force microscopic image on the right. Here there's 1, 2, 4, 5 magnetic states. Oops, sorry. Next. So we also beyond the n, we also play with the diameter. For example, we change the diameter of the nanodot from 100 nanometer to 600 nanometer. And we play with it, and apparently, obviously, the diameter can help us to modulate the window of the magnetic field to enable us to nucleate the skirming-like state. It's true for both n equals to 2 and both for n equals to 4. Of course, on the right side, we also discussed how the magnetic states would appear based on this magnetic schematics of the bottom layer and the top layer. For example, here, just for example, the antiferromagnetic state, which means the top layer, here the top nanodisk pointing downward, and all the bottom layers, which is a continuous layer pointing upward, right? So we also, it's a fundamental research that we try to understand the magnetic structures. So on top of that, those are all what I discussed before, or optical measurement. Eventually, we want to convert the magnetic textures, whatever different magnetic textures, into a readable electrical result. So we easily just build 4 contacts here in the whole bar, and we can just measure the Hall resistance, which is based on the effect of anomalous Hall effects. I can see that by playing with n and playing with the d, which is diameter, q, we can have different magnetic features or different magnetic transitions. It looks a little bit cloudy, but the signal is first we have different magnetic transitions we are able to capture different magnetic transition in electrical measurement, and it's also stable against the different n, d, and q. Basically means we play with the n, d, and q, we always can get this different magnetic states. Then, of course, we move a little bit one step further. So we also check whether it's stable in a wide range of the magnetic temperature. Of course, when you go down to the low temperature, we see it's a stable over a very wide range of the temperature. Of course, ideally, we also go to the higher temperature, but due to the limitation of our research capability, we cannot go even higher. So we only up to 300 Kelvin, but it's from fundamental research point of view, give us a little bit insight on the parameter or the strength of the magnetic interaction. We also, of course, summarized what we have already measured into a phase diagram. So on the vertical axis is the temperature, horizontal axis is the magnetic field. So from this phase diagram, we can immediately identify the range, the window that where we can get a skirming-like magnetic states or skirming bubbles. And this helps us to navigate through the phase easily. Here, then we also try to investigate deeply on how the magnetic structure exactly looks like, or how the spin texture exactly looks like when we have different magnetic states. In combination of the electrical measurement and MOCA measurement, we are able to identify how the spin would arrange at different locations. Especially if you look at here on the very right side, so we plotted schematics of the spin texture for different layers. Here is the top layer and here is the bottom layer. So we identified, or we correlate the electrical measurement, electrical Hall measurement result and the spin texture result, right? So we can see how this whatever this skirming bubble or skirming-like magnetic feature would evolve when we play with the magnetic field. This is for n equals to 2, when the bottom layers and bottom layer repetition is 2. We also studied the n equals to 4, meaning the bottom layer, as you can see from here, the bottom layer repetition is 4. We can see this is more interesting because we have more transitions here, and of course we also identified the magnetic spin textures here on the right side. And we feel that n equals to 4 would be the more interesting one because we can see a lot of features that we can potentially play with the magnetic states. So that's why we can potentially have a more magnetic states. For us, the more interesting one is here, this region. For us, this is this region, which is a skirming bubble region or skirming-like magnetic state region. So we want to see if we play with the magnetic field here, what we will get. So how we can generate some multi-state here. Here. Oops, sorry. Okay, here. So what we did was just sweeping magnetic field from a particular position and then go backward, right? So for example, we do the major curve or the green curve and stop, for example, at here. We go back from the orange curve. We see whether we can get some back to 0 to see whether we get some non-volatile states. When n equals to 2, the whole states, whole reversal curve or whole returning curve follow exactly the green major curve. If we change n equals to 4, we start to see something. You see this returning orange curve is not perfectly matching the major green curve. So we see probably you can do something here to have multiple, let's say, skirming bubble state. And we identified that n equals to 4 is a promising n number for us to get this. So then, of course, we play with it. And first, of course, on the major curve, we identify this. We identify the skirming bubble region, or there's a skirming region, and we just return from different places here. For example, on the right side. So following the dark green line here, this is our major curve. And we stopped, for example, here we return it, I will get this magnetic state. If we go to here, then return from here, of course, we can go all the way here. So it goes back and forth, it's already stated in that state 2. If we go from here, state 1, we go back and forth, we get state 1. And if, of course, if we go to the bottom state, or the state is stated here. As you can see that when n equals to 4 and d equals to 2, which is a particular interaction between the bottom layer and the top layer, so we can get multiple magnetic states. And we hope we can play with it and apply the information for future potential applications. But of course, for now, it's just very preliminary and it's very fundamental. And then now it is the conclusion. So we fabricated the nanodisk with array. We play with mainly the N space Q, and also we studied the multiple magnetic state in the nanodisk, and we achieved different states in the skyrmion-like spin textures. And they're stable when we play with the magnetic field. They're stable within the magnetic field window. And last, I would appreciate my collaborator in the fabrication and the characterization, and also the funding agent for supporting the study. And thank you very much.
Thank you very much for your presentation. It's now to open for questions and comments. Do you have any comments and questions?
Okay, I have some questions.
Please.
Yes, please.
So thanks for the interesting talk. So my first question is on the anomalous Hall effect. So
yes.
when you have a bottom layer which has a very large area and the top layer which is a small patterned dot. So when you do AHE, the majority of the signal is coming from the bottom layer or top layer.
Yeah. When are you talking about etching or measurement?
The measurement during the AHE, where is the majority of signal coming from?
Yeah. Sorry, when you say AHE, I heard it's etching. Sorry, my bad. Yes, this is a great question. I go back to the structure here. You're asking the question. This is my understanding of a question that when we measure device, apparently majority of the current will go through the bottom layer, because bottom layer is the layer that's connected to the electrodes. Mm-hmm. And you're asking whether we can probe the effect of these nano dots on top. Yes, it's a great question. And we also had this doubt before conducting the experiment. We also thought if the bottom layer is the majority, or shunt the current, and we will not be able to probe the upper layer magnetic small nano dots. However, when we did the measurements, we realized that the electrical measurement is actually quite sensitive to the upper layer nanodots. Basically, that means, for example, if we change, let's say we only have 1 or 2 nanodots on top. If we change the diameter, if we change the number of the nanodots, we can see the differences in the AHE results, number one. So that's a proof that we are able to see it. Of course, there's still a background of the bottom layer. On top of that, we also, when we flip the magnetization of the top layer, the nanodot, the bottom layer remains the same. Of course, this is the proof by the MFM. We can also see the results. We also see changes in AHE. So the conclusion is, although those are the nanodots on top, the AHE is able to prove it. Of course, you may ask a question a little bit a step deeper. Are we measuring directly the dot, or the dot influence the bottom layer? The question deep to that level, I'm not able to answer. So I'm not exactly sure whether we are measuring the top layer or the bottom layer, or maybe the combined upper dot and the bottom influence layer.
Okay, thank you. My second question is, people are trying to use the itinerant skyrmions for memory domain wall, racetrack kind of memory or the logic applications. Any use of the localized skyrmion?
Okay. Okay. So first, here, I just to your first question. So I'm not sure we are measuring electrically. We're measuring only here, or the combination here. Of course, current here only mainly flows here. To your second question, is talking about the people are already using the itinerary skyrmions for the states, and they are already, as proof in the Nature Electronics, there are a lot of studies. So what can we do with the localized skyrmion? To be honest, I'm not exactly sure. What I can personally envision is just the storage or the let's see, the conductance modulation. What I mean is here, these nanodots, number one can be used for storing the information, whatever up and down of the size. Number two, if we consider this one as kind of a synapse, so its resistance will be modulated by the external magnetic field. This is different. The conductance can be different, or maybe the whole conductance can be different. Then this can serve possibly synapse, but that's just the long-term vision. The exact design, I'm not sure yet. I'm being honest.
Okay, thank you.
Okay, thank you. Do you have any other question? We have plenty of time. Okay.
Also end a bit earlier.
Yeah. Okay, if not, I'm out of this field, but I'm very interested in your work. And when you change the N to 4,
Yeah.
What happens actually in the bottom layer? I couldn't get the
Okay.
the effect of the skirmion
Okay.
in the different layers. Yeah.
Okay. So let me first being honest why we did the experiments.
Mm-hmm.
Initially, when we play with the N,
Mm-hmm.
we were thinking of, for example, let me go back to the design. Okay, here probably.
Mm.
When we play with it, right? So this is N here, right? Yeah, this is N, changing the N, and we are thinking about play within the strength of the PMA below it and its interaction with upper nanodots. Then because we thought in the beginning, we thought if we play with this in a very ideal region, we can realize the 9 dots is a location specific flipping. What I mean is we can potentially flip this one first, and then this one next, and this one, third level. In principle, their energies are different. If we can push our energy, whatever the landscape there, so we can realize this position specific, so energy position specific switching, and introduce a little bit of perturbation or the randomness. So probably some, let's see, reservoir communications, reservoir computing may be achieved. That was our very naive, stupid design in the beginning. Later, we realized we could not achieve it. At least we were not able to prove it. So that's we have to fall back and see. We play with the N, and we just play with the strength of the PMA below it. And you asked, what do we really change? What do we really change is here. What do we really change is how strong the bottom, this region, would interact with the upper nanodot.
Right.
Roughly here. So how their, let's see, hand in hand, how strong they hold each other.
Yeah.
That was the idea. But
okay, but there should be some interactions between 2 layers in the bottom layers. So
yes.
Yeah.
Yes, they are interacting. Interacting with this green ruthenium layer. So this is a ferromagnetic, this is anti-ferromagnetic, and this one. And then we play with the magnetic field. We are playing, you can see from here, we are playing the size of this bottom, let's say, purple region. We force it a smaller kind of forming a small skirming. And of course, we play with the magnetic field. They will grow bigger and bigger. If it's small, they may ionize. They may be killed, and they grow bigger and bigger, and then they can influence the resistance, total conduction of the bottom layer, so that we can modulate the conductivity. Of course, the magnetization. That was the idea.
Okay. I think I understand the idea about that. Okay. So the other question is, why do you want to use the skirmion state? Why do I what? Yeah. Why do you want to use skirmion state? Okay. Instead of the more strong, digital states.
Yeah. First of all, we use the skirmion because it is a new phenomenon, new particles. We thought in the beginning, because it's new, we have some rooms to play with it or to explore. Because if we talk about the fundamentally well understood the ferromagnetic state, the antiferromagnetic state is being studied, I don't know, maybe in half centuries. We don't think we are able to contribute because it's already well understood. And we also thought we're not able to find something new. So that's why we aim for something kind of easier, the skirmion-based states. The second one is we realize that if we talk about the skirmion states, we believe they can grow bigger and smaller.
Yeah.
They can breathe, kind of breathing.
Right. Yeah.
If they're breathing, if they are stable, they can modulate the size by giving us different states. So give us tunability or ability to engineer. So that's what the thought.
So I think that because of the size changes, the physics will be very complex.
Yes,
because we want to use some resistance or a conductance, but the size changes, so it kind of non-linear effect goes on.
Yes.
So
that's why we are able to have some preliminary understanding based on micromagnetic simulation, but we are not able to go down to atomic level or real real clear quantitative picture.
So, but in the point of nonlinear dynamics, that will be good, because for the computation, we need some nonlinearity. So if it's memory, maybe not, but for computational device, it will be, good if you have some dynamics there. So
that was why in the beginning we were kind of, let's say, either naive or we have a very preliminary thought that maybe we could be able to achieve whatever reservoir computing or neuromorphic computing because of nonlinearity.
That's interesting. So one last question is the dependency of the device temperature. It is sensitive or it's Oh, this is one. Okay.
Yes. So thanks for the question. You're asking whether it's sensitive to temperature. Okay. Okay. The main feature of the anomalous Hall effect stays the same. So when we change the temperature, we mainly influence the coercivity. So that's why basically when we change to different temperatures, we have different let's see, windows, different sizes of the window for us to play with it. And let me be honest that why we did the low temperature measurement. We have the capability to go to the low temperature, and we did that. We tried to do that because we thought the low temperature may have less external thermal perturbation. We may be able to play with it easier, but it turns out that the room temperature is also stable. So that's why although we did low temperature, and because it's expensive to do it all the way at low temperature, so we did at the room temperature.
Yes. So structure is stable. Right? That's very interesting.
And we, of course, for the temperature measurement, we may be able to extrapolate to get a more understanding about anisotropy, the Hall coercivity. But it's a fundamental parameters.
Oh, interesting. Good. Yeah. Okay. Questions from me is over. The other people.
Thank you very much.
Thank you. The people have any other question?
Yeah. Hi.
Yes, please.
Yes, Prof. Ranshuk, may I ask a question?
Yes, please.
For your previous slides, where you have shown this phase diagram, the nucleation of skirmion or the skirmion's area which it exists, it requires a certain external magnetic field. Okay. Okay. So I thought in the case of having a multi-layer structure, because when you're talking about using it for memory or something, the main idea would be to include exchange biased or something to get skirmions at zero field, actually, where you don't have to apply any outer stimuli. So in your case, since you are already working on number of multi-layers, have you thought of introducing such a zero field? Because the field where I might be wrong, because that in your phase diagram, you're getting it on around 6,000 Oster or something like that, which is quite high.
Yeah.
Okay, around 2 to 3,000. Yeah. So where do you see, like, how can you modify your structures to get near zero field?
Yeah.
Yeah.
I understand your question is, I totally agree with you that we'd like to have skirmion stable at the zero field. That's my understanding of your question. And indeed, we want to have that. So basically the skirmion states close to zero, so which will be easier for future applications. We tried that, and just unfortunately, we are not able to push this window to be here. It's determined by the fundamental interaction between the top layer, bottom layer. So we realized that when we play the magnetic field, we only push it to this temperature, this magnetic field window, we can have small skirmion-like magnetic features. Also, first of all, I need to admit that I'm not 100% sure this is a skirmion. So that's why we always say this is a skirmion-like textures. We know it's a small dot, it's a circle-like, it's from MFM it looks like a skirmion, but we don't know exactly it is a skirmion, right? We just feel from simulation point it looks like a skirmion. And you're talking about how to push this to this region. To be honest, we don't have a clear design yet. We don't know how to push this to this region.
Okay, thank you. So time is just came. So thank you very much again for your nice presentation. Thank you.
Thank you for the question. Thank you for the host.
Thank you. Oh, let's move on to the next speaker. Next speaker is the Dr. Nurifan Matthews. Maybe not the exact pronunciation for your name, but from the NTU Singapore. If you're ready, could you start your presentation? Now we can see your slide, but it's not the presentation mode.
Sure. I hope that's fine now.
Oh yeah, very good. Yes, please start.
Thank you for the invitation to present our work here, especially to Professor Permanayagam. I think other neuromorphic approaches is probably the best way to put our work, because we don't really exactly fit in with the rest of the work that is shown here. However, I still hope our work is of interest to all of you. So my name is Nurifan Matthews, and I'm a professor at Material Science and Engineering, also at the Energy Research Institute. So my talk would be on a different material system than most of you have been discussing here, and that's on the specific one called halide perovskites. The properties that we exploit for neuromorphic applications are its ionic and electronic properties, and especially the coupling between the ionic and electronic properties. The work that we present is still pretty early TRL level work, but we are studying the materials, the devices, and the mechanism, and trying to correlate more and more to the different neuromorphic applications. Just to set a bit of a background, although most of you are familiar with this, well, almost all the recent progress for designs for next generation electronics is designed to make machines intelligent like humans, work with less supervision, work with more complex problems, etc. And the reason why we do this is if you compare bio-inspired computing, or let's say what happens in our brain versus classical computing. As we all know, classical computing is very good at crunching numbers based on rule-based reasoning. It's very good. Repetition of well-defined actions is always very, more or less established. But what a lot of challenges of making computers look like, think like humans is because of the unstructured data that we humans normally process. So we are very good at pattern recognition. We can handle vague and incomplete information, and we can adapt and learn. This kind of this is the motivation, from a really zoomed out point of view. This is the motivation why a lot of neuromorphic approaches exist. And if we go into smaller and smaller details, as some of the speakers have already shown before, the conventional electronics is based on the von Neumann architecture, where the processing and the memory are separated, and there is a shuttling between each of them as you do simple processing. So this is okay for many of the applications that we have, but what a lot of people theorize is that if you want to go towards neuromorphic applications, you need to co-locate the memory and the processing, just like the human brain does. So the attempts, as you know, is to form neuron synapses and networks in memory computing. All these approaches, derive from this effort to make neuromorphic electronics, which make electronic devices and software which behave like the human brain. Of course, silicon CMOS devices already exist. So this is the old, now pretty old True North chip from IBM, and now there is the Intel Loihi chips as well. So the True North chip, for example, was able to simulate emulate 10 power 6 neurons and 10 power 8 synapses. However, although this is impressive and a good milestone in the area, it's still very far away from the human brain. So even if emulation of the human brain would be possible, it definitely requires 6 orders of magnitude more neurons, 7 orders of magnitude more synapses to be emulated. And the challenge, which I think not a lot of people work on, and we also don't work on exactly, is on the interconnectivity part of it as well. So the way our team came into this area was to try and see whether we can make simplified architectures. And that's because, let's say, if you take a simple representation of a synapse, there are many representations of CMOS synapses. So one synapse over here requires 3 capacitors, op-amps, etc. Right? Can we make it simpler? Can we make it with can we make it with a new material and new device architecture? Can we make it simpler? Can we reproduce a synapse with one device, for example? So that's the logic behind our work. And broadly, most of the stuff that we make in our group are Memristors. So as you all know, Memristors is the 4th basic element, both basic circuit element. It's essentially a resistor with memory. So most Memristors are 2-terminal Memristors, and when HP when HP published the paper on Memristors, they were initially talking about TiO2 based systems. There is still controversy and confusion as to whether it's really a true Memristor, etc. But that's not key to this presentation. So the state-dependent Ohm's law essentially is what the Memristor does. And since it's a 2-terminal architecture, a lot of the expectation is that it can be scaled down to very small dimensions. So there were recently some papers where they have scaled down to 2 to 3 nanometers of a Memristor, of an individual Memristor. So all these are the advantages of making Memristors. And there are different types of Memristors, and they're useful for different applications. So I hope to show you some of that over here as well. So you look at non-volatile Memristors. The most common Memristor is a binary or a digital Memristor, where you have a high resistance state, and which, when you apply a forming voltage, you can switch to a low resistance state. So you have 2 resistance states, R1 or R2. This is a binary or digital Memristor. There are analog-based Memristors where you can control the resistance states with multiple resistances, which is what a lot of synaptic applications need for the weight update or the weight change in the synapse. You want to have different resistances or different conductances that strengthen or weaken the connection between the different neurons. And you also in certain applications want volatile Memristors, which can have 2 different states, but on removal of the voltage switches back to the older resistance state. because it's not necessary to just learn. You also need to know how to forget or reset the system as well. So different kinds of memristors are needed, and our group has been working on trying to emulate these different types of memristors. The use cases for memristors are pretty broad. And this is from a paper written by, I think, Abu Sebastian from IBM in Nature Nanotechnology, where they looked at where memristors could be utilized and classified according to the precision that they need, as well as the computational complexity. So a lot of the advanced oxide memristors are trying to look at deep learning based approaches and trying to see whether deep learning can be accelerated by these memristor networks. But there are lower hanging fruits as well. For example, random number generation, image filtering and compression, etc. So this is the broad picture of how memristors are being utilized. And in terms of, if I zoom in a little bit more, there are two specific use cases that the community studies for memristors. One is in this crossbar array fashion. So assume at each junction that there is a memristor or a two-terminal device over here. So when you apply voltages at each row, and then you sum up the current across this particular line, this is actually a dot product. So the total current flowing through here would be the voltage multiplied by the conductance of the memristor plus this voltage, etc. So trying to embed, so you have a more or less direct emulation of a vector matrix multiplication within this crossbar array. And such multiplication is very common in many of the algorithms that are used for deep learning. More closer to what we work on, try to work more on the biological learning rules and trying to emulate the biological learning rules. And that essentially means that we are normally working with spikes. We are looking at the intensity of the spikes in some cases, but most importantly, the timing between the spikes as well as the frequency of the spikes. Since because this is how the brain seems to work as well, and working with spikes also means the power that you utilize is lesser because your device is not on most of the time. So when we first actually came into neuromorphic devices, we did not work on two-terminal memristors. I mean, to be frank, we were working on transistors, and what we realized was our not so good transistors are actually closer to a synapse, and that is how we kind of went into synapses. Because we are trying to play around with new types of oxide materials for transistors, and we realized that these trapping kinetics can be useful for synaptic applications. So let me just briefly explain the device structure over here. So this is a thin film transistor structure. So in a thin film transistor structure, normally you would have a semiconductor. In this case, we are using indium tungsten oxide, which has been sputtered on top of a dielectric, and the silicon over here is highly doped, so acts as a gate. The ITO electrodes over here acts as electrodes, the source and drain of a transistor. So once you apply a positive voltage over here, electrons accumulate on this indium tungsten oxide and the transistor turns on. So over here, you can see that the resistance is low at negative gate voltages, and above a threshold voltage, the transistor turns on and there is a lot of current through it. It's a TFT, so works in accumulation mode, unlike MOSFET, which works in inversion mode. So what we did was take this conventional transistor, and we actually built one more gate on top of it. So what we put in was a solid state ion gel on top of it, which itself is a mixture of this particular fluorinated polymer and this ionic liquid, and then the silver as a top electrode on top of it. So what we have is essentially two gates which could act as presynaptic terminals, and the source and drain electrodes could act as postsynaptic terminals. This is the transistor or the conventional testing when you use it with the bottom gate that's given over here as electronic mode. And if you use it over here in the ionic, we sometimes call it ionotronic mode, or basically the top ion gel mode, you can see that this is the characteristics here. One thing you can immediately see is that the voltages, the operation gate voltages are very different for both the modes. So the electronic mode, we have to apply 10, 20 volts, while the underlying ionic mode happens at much lower voltages. So we decided to, so this electronic gate, we could kind of make it a global gate, and we could have multiple transistors or multiple synapses connected to it, while the ionotronic we would individually probe or individually control as well. So based on the interplay of the hysteresis between the ionotronic mode as well as how much the threshold voltage can be moved, we could use it as a proxy for plasticity, or the total amount of current or the conductance of this channel, this indium tungsten oxide channel over here. So based on that, we are able to modulate the conductance states of the indium tungsten oxide by applying, so we can have it, so the global mode is the electronic mode that is shown over here, so that is limited. The local ionotronic mode can actually have much more long-term weight change, while the dual gated mode, where we apply both of them, add on top of each other, gives us the largest weight change. Because ion gated mode is operating at very low voltages, and if you work with small enough pulse widths, your energy consumption per spike can be very small. But again, please note that the pulse widths that we normally work with are still pretty big. Initially, they were limited by the kind of Keithley's or the electronic equipment we were utilizing. Now we are moving on to trying out faster and faster pulse widths. So this was so in this case, the key factor to remember here is a lot of the synaptic characteristics is due to the dynamics of the ions within this ion gel, which is kind of similar to what happens in the natural synapse as well. So working on this thin film transistor configuration, we actually added on one more gate. So in this work over here, I had two gates, the top gate and then the bottom gate over here. In this particular work, we worked with a 2D material which has photoactive. So we technically can use a photonic gate as well. So we had a bottom gate control, we had the top gate ionic liquid control, and since the ionic liquid is transparent, we can also do optical control. The reason why we went for optical control was because the amount of charge carriers you can induce in any semiconductor by gate voltage is finally limited by the breakdown strength of the dielectric you use, either the breakdown of the SiO2 or the splitting of the ions, the ionic liquid, etc. While with light, you could actually induce much more number of charge carriers in a semiconductor. So by interplaying the electronic, ionic, and the photonic, we are able to show that we can modulate the learning and forgetting rates of this device. We can also have long-term memory with the optical states. And again, since so that's an interplay, because when you excite charge carriers over here, the carriers can get trapped at the interface over here, can continue to stay on the channel due to the ions accumulating on top of the channel, etc. So there are multiple intercoupling that can be done. And the fact that it is a 2D material is also helpful because it's an ultra thin channel. So you have very good control over the carriers in the system. So showing these optical effects can actually increase and control the synaptic characteristics. We actually went ahead and did even more work. So in this work, we used rhenium sulfide transistors. Again, conventionally their mobilities are 26, etc. But what we found out was that the persistent photocurrent effects in these systems. So once you shine the light or apply an optical pulse to it, the current initially spikes, as can be shown here, and then kind of saturates. And this control can be very nicely performed. So we showed that the conductance level of this kind of transistor can actually be, we showed about 980 states in this kind of a transistor controlled by the light. And we also showed that you can increase the conductance by the light, and then you can erase it by applying the voltage. And we also showed how different amount of, the sensitivity of this material to different wavelengths, which could also be utilized for example, selective control of one synapse while not actively controlling another device, etc. You guys can, if you are interested, you can read the details in this particular paper over here. So but even when we were working on these 3 electrode devices, and although we were pretty successful in making them work, what we always knew was that many of the dynamics that we see in these transistors actually don't really come from the semiconductor, but they actually come from the ionic dielectric that is sitting next to the semiconductor. So we definitely wanted to go towards a system which had ionic electronic coupling. So in my other work, I work very heavily on halide perovskites for solar cells. And we decided to focus on these material systems as well for neuromorphic applications, because these guys are ionic semiconductors as well. This is just to briefly introduce what a halide perovskite is. So the perovskite structure is a standard ABX3 structure. Most perovskites that is utilized in physics is the oxide perovskites. What we have is a halide perovskite. So the X is normally a halogen. The A site is a mono positive ion. So it can be cesium, it can be even methyl ammonium as shown over here, or any small chain organic compound. And the B for the optical applications, lead is the one that is utilized. Lead 2 plus is utilized, but you can do tin 2 plus and other kinds of material systems as well. I will talk about the different possibilities there. So the reason why it is exciting is because these systems are processed very simply. You do not need very high temperatures to form it. You do not need super expensive equipment to utilize it. Just like you spin coat your photoresist, you can spin coat and form this. You can evaporate and form it as well. And although they are formed in such kind of rudimentary methods, the electronic properties is pretty good. So the electron and hole transport lengths in these systems are pretty high. Because of the electronic structure, the absorption edge is actually very sharp. So sometimes we joke about it, it's like 3-5 semiconductors, but solution processed. And by substituting the A and the X, you can change the band gap. So over here, if it is the iodide halogen, then the absorption edge is at 800. But if you substitute the iodine with bromine, you can see that the band gap can be changed as well. And you can have more or less continuous variations in the band gap within the system. So the processability as well as the electronic properties is why a lot of people work on it for solar cells. And the efficiencies of these solar cells are very high, comparable to silicon, although perovskite is still very young, and the sizes in which these solar cells are shown as very small. The reason we focused on it for these material system is the problem that we face in the solar cells is of ion migration. So as I mentioned, in all these kind of devices, it's the ionic activity that gives us all these neuromorphic phenomena. And here we have another material system that has ionic and electronic activity embedded within it. So for example, if you take, in this case, let's say 7 or 8 different types of halide perovskites of different composition, you shine light on it for a long time, you can see that the compositions have transformed into a few compositions. If you make a light emitting diode out of these systems, and after a long time heating, the color of these systems change. And the color of systems changing is synonymous with the halogen segregating within it. So even if you take a mixture of many halogens, a mixture of different components, and then you heat it up, you could have iodide-rich areas in certain location and bromine-rich areas in certain location. So ionic activity is the ionic motion is definitely active within these material systems. In our group, we exploited this first for solar applications. So so as I mentioned, we don't need to necessarily use lead. We can use other types of material systems as well. So we were working with antimony based systems. Here is an antimony halide system. So a normal solar cell does not just have the semiconductor alone, it has a selective layer on either side, so that only holes go in one direction and electrons go in another direction. So what we did here was to make sure even though there is no selection layer on either side, the material just acts as a simple photodetector. When you shine light on it, the light just passes through the current just passes through the 0 volt. But once you apply a polling voltage, you can see that you are able to switch it as such that there is an inbuilt voltage within this system. And this inbuilt voltage comes because when you apply voltage for a long time, the halogens can start to diffuse within it and start to dope one end p-type and another end n-type. So you could have a self-doping kind of mechanism active within these perovskite systems, which again gives us another knob to turn to try and utilize it. So in our initial studies on utilizing it for memristors, we just put it, a metal electrode directly on top of the halide perovskite, which was directly on top of an ITO electrode. And we compared 3 different types of perovskite. MA is methyl ammonium lead bromide. FA is formidimium. These are both organic ions. And cesium is, well, the metal cesium. So when you make this kind of simple architecture, you are able to form a simple 2-state system, which is good, but not necessarily so useful for neuromorphic because you want to have multiple states. So what we did was to add on other interfacial layers. So we still use the same halide perovskites, the 3 perovskite layers mentioned in the previous slide. And we have electron transporting layers and the hole transporting layers added onto it. So these are the different layers that we added onto it. And then the logic we wanted to try and follow was, we know that halogens are active, the halides can move within these perovskites. We know that the p-type and n-type doping can happen. We also suspected that halogens would be able to move into the interfacial layer and dope it. So could we utilize the interfaces to do analog type switching? So we were successful in doing so, and we were able to emulate the different learning rules, including the spike time dependent plasticity, where depending on whether the postsynaptic pulse or the presynaptic pulse arrives first, you are able to modulate the weight changes. We were able to study this for all the different materials, and we were able to see that the synaptic activity seems to be stronger for the organic based one rather than the inorganic based one. And again, remember, just to recap, so normally a CMOS would require a couple of capacitors and op-amps to do such a simulation, such an emulation, while what we are doing with a single device. But again, to be fair, every memristor would be able to do something similar. So in order to understand what is happening over there, we also did DFT calculations to understand the activation energy for the diffusion of the ions within it. So paradoxically, MA and FA, which have the higher activation energy for diffusion, seems to show us the most stronger effect. And that we suspect is because the cesium, which should diffuse more easily, and bromine, which also should diffuse more easily, can also relax back fast. So in the time scale of the measurements that we are doing, MA and FA pop up because they are the ones that have not self-diffused back into their locations. And that is how we are able to see stronger effects for these kind of perovskites. Going from, so we went from a binary or digital memristor to an analog memristor. We also wanted to explore whether we can do volatility can be controlled in our memristors. So what we did was to again work with this perovskite MAPBBR3, except we changed the interfaces. So on one case, we use this P.PSS interface, and in another case, we use this nickel oxide interface. The P.PSS and the nickel oxide interfaces behave similarly at low voltages, but at high voltages, you can see that the P.PSS still remains volatile, while the nickel oxide starts to switch to abrupt system. So the P.PSS, so the same perovskite similar thicknesses, maybe try to control it to be exactly similar, etc. The P.PSS interface would read to diffusive or volatile behavior, while the nickel oxide interfaces would read to non-volatile behavior. And the reason for that turns out to be that when we are applying a voltage, so this is on the top is the SEM images for P.PSS, below here is nickel oxide. We are able to see that under the application of the voltage, there is actually a reaction that happens between the nickel oxide and the perovskite at these interfaces. So the formation of lead bromide at the interfaces could be the reason why we have such an abrupt switching characteristics for the nickel oxide, while the P.PSS was more milder. So we utilize both these types of perovskites in something called nociceptors. So normally we talk about synapses and neurons, but in the human body, the pain receptor that we normally that is utilized is something called a nociceptor. So a nociceptor is essentially a modulatable filter which does not have long-term memory characteristics. So it can so if the input voltage, so if you translate it to electrical parlance, if the input stimulus is above a particular threshold, it acts as it can be classified as noxious, and the current response can be magnified, while if it is too mild, it won't respond. But there are also other characteristics such as allodynia, hyperalgesia. So for example, when our hand is damaged, or let's say we have had a fall, even a gentle touch can trigger pain, right? So that is because we are kind of sensitive at that moment. So allodynia is when the pain occurs to a stimulus that normally does not evoke pain, etc. So these kind of characteristics could also be seen by our devices. The thresholds, essentially there is a tunable threshold when it is damaged that triggers, that shows all these kind of behavior. And of course, so this is for the P.PSS based perovskite devices. The nickel oxide based perovskite device acts more like a conventional synapse, and you can again show STDP characteristics, etc. So now that we have two types of neural elements, what we decided to do was to try and do kind of a demonstration whereby which we could have sensors. This, since we are talking about pain and pain sensation, we would utilize pressure sensors. They would be connected to nociceptors, that are the pain receptors, synapses that could provide local memory, and then connected to CMOS neurons, which could be connected to an actuator like a robotic arm, for example. So this would kind of go towards the concept of in-sensory computing, whereby which the computing happens right at the sensing edge before the information is passed on to a central processing unit, etc. I'll try to go into details of this a bit later on. So if the video is playing, I hope the video is playing and you guys can see it. Does the video load for all of you?
Yeah, we can see.
Okay, thank you. So over here, we just took a simple robotic arm. There's a pressure sensor embedded on the other side of this hand. We have artificial synapse, perovskite-based artificial synapse over here, a perovskite-based artificial neuron over here, and a CMOS neuron under this yellow box. The logic that we had was that when you when you press the hand too much, it's like a noxiousness occurring, and the pain signals. So if you, okay, the video is loading. So when you press it very hard, there's a response because the nociceptor recognizes it as pain. But if the nociceptor is disconnected, as you saw happening now, when you press it hard again, it doesn't recognize it. But so then we reconnected the nociceptor and the whole network connection, and then we trained it. So we pressed it roughly 2 times, and now we are making sure that the synapse programs or learns that the high pressure is a bad thing. So this is the training still occurring. The advantage of having this artificial synapse is that because you have local memory, even though now the system is disconnected, it still retains the memory that extremely high pressure is not good and it moves again. Okay, so it's a bit hard to pick up from the video, but the synapse is acting as a local memory. The nociceptor is acting as as a filter in this case. So we've been able to do such simple demonstrations of these particular devices. So since I'm running out of time, I just want to end a few slides on why we would still continue to work on halide perovskite based devices. So I alluded to a little bit about how ion migration is very prevalent in halide perovskites. But there's a lot of tunability that you can do with this system. So there's a lot of chemistry you can play with this. You can substitute your cations, anions, you can passivate it. You can control the amount of vacancies that you can create in these different types of material systems. And we've been working only with electronic based synapses, but technically you can make ferroelectrics out of this. You can make magnetic perovskites, etc. as well. We would not be exploring it presently, but this system is very versatile. But this also means that we have a lot of challenges, and we need to understand a lot of the materials mechanism device correlation is still pretty new. So if you zoom into a halide perovskite memristor, and this is the architecture that I talked about. So normally we always have a hole transporting layer and electron transporting layer sandwiching the perovskite layer. So on the application of a voltage, the halogens, the X minus the halogens or the A side cation can start to diffuse. So you could have ion migration within the perovskites. Halogens can diffuse into the interfacial layer and can lead to electrochemical doping. That is a mechanism that we can utilize. There is conventional electron and hole trapping at the interfaces that we can utilize if you which could be active at a different time scale than the ones that we have been exploring so far. And of course, you could have the filament formation, which a lot of normal memristors have as well. So under what voltage, time scale, and material combinations does these mechanisms do an interplay is something that we intend to explore in the future. The second challenge is, although I've talked about, I think, just 3 compositions of this particular perovskite system, there are a huge number of perovskite related systems. So these are not exactly perovskite structures, but they are again have the characteristics of being processed very easily from solution processed, etc. So with so many different combinations of systems possible, as well as on top of that interfaces, we need to also study, we need to also have a rational way of understanding what are the character or what are the compositions that can lead to better memory. Which is why we are also planning to do self-driven synthesis of these material systems where, let's say we would have a robotic system, because it's a solution processable material system. It's pretty straightforward to make a different composition. So utilizing different precursors, we can do automated solution preparation, deposition, and then measurements. So we will not be able to measure directly the ionic properties, for example, but we'll have to measure something that is a proxy for ionic transporting. So, how quickly does the electronic transport change for 10 pulses, 15 pulses, which is an indication of how, mobile are the ions within the system, etc. So this is something that we would be exploring as well. Another thing that we have not stepped into, but again, it's something that is unique to perovskites, is how you can process it very easily. So again, I don't believe the future of perovskites lie in CMOS or lie in competing with CMOS, etc. I don't think it's that possible. But there are other applications where you could look at utilizing
maybe we should, take some questions. We only have
I am at the
2 or
last
3
slide.
minutes.
I'm at the last slide. Yeah. So in our systems, we can print these perovskites very easily. In this case, it's like a 10 cm by 10 cm printing. Technically, we can go larger area. So what we are trying to see is whether these kind of printed large area memoristive systems could fit into environment where the large area memoristive systems can do neuromorphic pre-processing that can then feed into a neuromorphic chip later on. So we are not planning to compete with the neuromorphic chip, but looking at things how we can pre-process the data before it can pass on to the neuromorphic chip. So this is what we talk about trying to do in sensory computing. All right, and thank you for your patience. So this is the final slide. Acknowledgement. We are a materials group, so we had to get a lot of help from Professor Arindam Basu, who is a neuromorphic expert. Rohit was my first PhD student who did a lot of this work. Timothy is presented yesterday on some of his oxide-based work, and these are the other folks who help out with the perovskite compositions, etc. And finally, the acknowledgement of funding from Ministry of Education, Singapore. I hope I've not overrun my time too much. Thank you for your attention so far.
Thank you very much. Actually, we have only 3 minutes. Thank you for
I'm sorry. Yeah.
very interesting talk, but I think many people have many questions, but I can take 1 or 2. Do you have any question?
Yeah, maybe
Okay.
I'd like to ask one question.
Please.
A very interesting presentation and a lot of very interesting work. Why people don't talk about constructing neurons using these kind of materials?
Yeah, we are attempting to do that. So memristor-based neurons exist. Oxide memristors, people use exploit negative differential resistance, etc., to make neurons. So that exists. In perovskites, I don't think anybody has made till now, but I don't think there is anything fundamentally against preventing it from being utilized for neurons. Although I talked only about the materials part of it, there's also device-related factors that you need to consider, including the capacitance of the devices that you utilize, etc. So if you design your devices appropriately, I don't think neurons are impossible for these material systems. It should be doable. And we intend to do it, yeah. I mean, not yet, but yeah, we intend to do it, yes.
Okay, thank you. So when you are applying gate voltage, you are directly applying the gate voltage below the silicon substrate, is it?
You could do it like that. So, I mean, normally our chips, I mean, you can wire it up in any way possible. So normally, so we made arrays of, let's say, 36 by 36 transistors and things like that. Some cases it's below, some cases it's side gate and things like that. So it's not so much of a determinant for our results. Yeah.
Okay, thank you.
Okay, thank you. So for the last question, I think Dr. Kumar has a question.
Hi, Prof. Thank you for the nice talk. So in slide 14, you said when you apply the gate voltage with ionic liquid. So I was wondering, is it the conduction of the only ionic liquid changing between the gate and source, or also the layer below the ionic liquid?
We don't particularly think the ionic liquid is. So the gate voltage is just forming the electrical double layer at the interface of the source and the drain. So we also try to, the gate voltage is kind of separating the ions and forming the electrical double layer at that interface. Between the source and the drain, we don't think the ionic transport is occurring so strongly. First of all, the concentration of the ions that we utilize is lesser and the electronic conductivity of the underlying layer is much higher. In certain cases, we have actually blocked the source drain electrodes such that they don't contact the ionic liquid as well. So we initially did some studies on that and then saw no difference whether we block it or no block it. But so we don't think the ionic transport in the ionic liquid is playing such a huge role. It's the ionic electronic coupling that seems to be the biggest factor for us.
Thank you.
Thank you very much. Just running out of time. Sorry about that. Thank you very much again.
Thank you again for inviting us. Yeah.
Okay, let's move on to the third speaker. But third speaker has been changed recently. So I'd like to introduce Professor Wei Chao Yu from Fudan University, China. Are you ready?
Yeah, can you hear me?
Yeah, sure. Yeah, good.
And can you see my screen?
Yeah. So
Okay,
could you
thanks.
please start your presentation? Thank you.
Yes. So first of all, thanks for introduction and thanks for giving me this this opportunity to give a talk here. And let me introduce myself first. So my name is Wei Chaoyu, and my current affiliation is the Institute for Nanoelectronic Devices and Quantum Computing, Fudan University in Shanghai, China. Today, my topic is intelligent magnetic textures. This work was in collaboration with Professor Zhang Xiao, also from Fudan University, and with Professor Garrett Bauer from Tohoku University. This work was mainly done when I worked in Tohoku University. Since there may be many beginners just like me on YouTube channels, so let me go through some basic background. As a human being, we can easily perform the task of classification. For example, when we see a picture of a cat, we say the number 1. And if we see the picture of a dog, we say the number 0. We can easily speak out the number for a given picture. The whole process is accomplished within our brain, which is just a black box. In order to perform similar functions in digital computers, computational scientists, they invented the model of artificial neural networks. An artificial neuron is the minimal element in neural networks, whose value y is calculated in this way. So where x1 and x2 are values from other neurons, and w and theta are weights and the local bias. Furthermore, we need an activation function, f, to induce nonlinearity, such as a sine function and a sigmoid function. If we connect multiple artificial neurons layer by layer, we will have a neural network, which has a very high degree of freedom and very strong nonlinearity. So here we only have 2 layers, but in principle, a multi-layer neural network can do everything. One special type of neural network is the Hopfield network, which will be the main character in my talk. It's special because each neuron acts as both input and output at the same time. The value at the time step t becomes the input for other neurons at the time step t plus 1. So this is a dynamic network. We can write down the so-called energy function to describe the state of the network. The mathematical form is extremely similar to the well-known Ising model, Hamiltonian. So here the value y is equivalent to the spin, sigma, and the weights w is equivalent to the exchange interaction j, and the bias theta is equivalent to the Zeeman field. Since maybe people are familiar with the dynamics of Ising model, let me introduce. Let's start from a 1D spin chain. And then let's assume the ground state of the spin chain is a uniform magnetization. If we randomly flip one of the spin, the system will increase its energy and finally evolve back to its ground state under finite temperature. We say that the system can correct itself in the presence of external perturbation. The Hopfield network can perform similar function and is widely used as associative memory. For example, this is a picture memorized by the network. And if we remove or modify part of it and input it back to the network, it will finally recall the stored pattern, but sometimes it may fail. There are actually 2 stages for working neural network. In the first stage, the training stage, we do a lot of work to calculate and modify the weights, just like we are preparing for the exam. The aim is to have an outstanding performance in the second stage, the inference stage, where we need to output results. We need to output correct results with fixed weights. The spirit of neuromorphic spintronics is to replace these mathematical models with spintronic devices. For example, we have spin torque oscillators whose output is a nonlinear function of the input DC current. It can be used as spintronic neurons. And we also have spintronic memristors whose resistance depends on, for example, the position of a domain wall and the number of skirmions, which can be used as spintronic synapses. So far, all these devices have been successfully applied in the inference stage, but for the training stage, we still need the help of traditional digital computers to calculate the weights. So the motivation of this work is to look for a physical system which can train or learn by itself. This is not a big deal because most of the memristors and most of the phase change materials, they can perform this task. So furthermore, we hope that the learning rule is governed only by physical law, which is not designed by us, by human beings. Our candidate is the magnetic textures. In magnetic systems, we have varieties of interactions such as exchange, anisotropy, demagnetizing field, and Zeeman field, etc. In order to minimize the energy, the ground state is no longer uniform. There will be magnetic textures such as domain walls, vortex, skirmions, etc. Our interest today is the maze domain, so-called maze domain or labyrinthine patterns, which is stabilized by the chiral Gyroshin-Skin-Mori interaction, DMI. So here, the white and black color represents the out-of-plane magnetization, and the arrows are for the in-plane components. What is going on? What's the physics lied in such a physical system? So firstly, we have anisotropic magnetoresistance, AMR, which means that when the current flows through the magnet, the resistance is different depending on the alignment of magnetization. In the presence of AMR and such a complex texture, we will have a general Ohm's law, where the conductivity is no longer a scalar but a tensor, which depends on the specific magnetic configuration. Secondly, we have spin transfer torque, STT. So when the current, the spin, the electrons flows through the magnet, the spin carried by the electrons will interact with the local magnetization. Which can induce the so-called spin transfer torque, which means the magnetic textures can be driven by the electric current. So briefly speaking, when we apply electric current, it drives the texture, leading to the change of the conductance state. And let's see the simulation. So this is a micromagnetic simulation. For this square film, we apply voltage difference on the left and the right edge so that the current flows from left to the right. So the left figure plots the magnetization configuration, and the right one plots the current density. In the presence of spin transfer torque, we can see that the stripe domains, they will finally be aligned perpendicularly to the current, and it finally becomes stable after sufficient long time. So as we have mentioned, in the presence of such kind of AMR, the conductance state depends on the magnetic configuration. For example, the conductance of a Bloch wall and a Neal wall will be different. So we can calculate the conductance of this film at each time step according to that simulation. And we can see that the blue curve here is the horizontal conductance, which is calculated according to the left and the right edge. It increases with time and finally reaches saturation. The red curve stands for the vertical conductance, which is calculated from the top and bottom edge, which decreases in an almost symmetrical way. This feature indicates that the magnetic textures have so-called plasticity and can be used as artificial synapses. Now we start to construct a Hopfield network. This is the model of a 4-node Hopfield network. We have 4 neurons connected by each other with certain weights. To design a hardware version, we assume a disk film with the magnetic textures, and we consider 4 electrodes. Actually, this configuration is very similar to the one mentioned by Professor Ackerman at the first day of this workshop. He also considered the 4 nodes system. So for such a system, when we apply voltage on each electrode, we will get a current flowing into or out of them at the same time. This process is governed by the Kirchhoff's law. So now we have a hardware Hopfield network because the voltage can be treated as input and the current can be treated as output. The weights connecting between input and output are now encoded into the conductance state of this magnetic field. As I have mentioned before, we can write down a Hamiltonian to describe the state of the network. And also we can write down the so-called energy function for the software level Hopfield network. Similarly, we can write down according to this software version and write down the hardware level Hopfield energy function for the Hopfield network. So here, the voltages are the inputs, and the conductance matrix stands for the weight matrix. So now this mathematical equivalent effective energy function is no longer a pure mathematical expression. It has a physical meaning because it has the unit of power efficiency, which can be detected through experiments. So now let's move to the training stage. How to train this Hopfield network? In conventional way, we need assistance of digital computers to calculate the weights, and according to those machine learning algorithms, and then allocate those weights back to our neuromorphic hardware. But in this work, we perform training by feeding directly feeding the correct answer to the system. For example, now we are going to store 4 pixel binary patterns. Let's say plus minus, plus minus. What we do is to apply the corresponding voltage on each electrode in, let's say, in a clockwise way. According to Kirchhoff's law, the voltage difference will generate currents flowing through the magnetic field, and the currents will drive the magnetic textures because there's spin transfer torque. After a sufficient long time, the texture will finally become stable, and we say that the training is finished. And then we can obtain the conductance matrix according to the configuration and calculate the energy function according to all 16 combinations of the inputs. It's clearly seen that the energy function reaches minimum for 2 states, for the state minus plus minus plus, and for the state plus minus plus minus, which means now the ground state of this network is modified after training, and the texture has successfully memorized the pattern we feed to it. So for a 4-node binary network, we have totally 16 different inputs. But according to the symmetry of the patterns, we have only 3 non-trivial states, and this is 1. And here I plot the remaining 2 non-trivial states. So we can see that for arbitrary input, the texture can finally adjust itself so that the inputs become ground state of the 4-node Hopfield network. However, there are two exceptions. When all the inputs, when the all input voltage are positive or negative, there will be no voltage difference and there will be no current flowing through the magnetic field, so the training cannot be performed. And in application, we don't have to calculate the energy function every time. The stored pattern can be retrieved via very standard inference process. So I will not go into details in this part. The key message of this slide is that after training stage, all the weights are stored as this conductance matrix inside the magnetic field, and it can be retrieved easily by different methods, such as synchronous, asynchronous, or annealing methods. And the approach proposed in this work is very different from conventional ones. One of the most popular and successful architectures for neuromorphic computing is this crossbar array. So where the weights are encoded into each single memristors, so that the weights are independent and they need to be updated separately. In order to calculate weights, we also need external algorithms, and in order to update weights physically, we need empirical information. For example, the current voltage relation of every single memristor. And in comparison, we propose the proposed device here is similar to the so-called horizontal resistive layer, so that the weights, they are correlated, and the weights can update physically according to the external stimulus, namely the pattern to be memorized. Most importantly, the learning rule here is natural and intrinsic, which is governed only by physical law. So let's discuss more on the learning rule. The principle of learning comes from neuroscience. According to this Hopfield theory, that cells that fire together wire together. So inspired by this principle, computational scientists they developed such algorithms such as Hopfield's rule or delta rule, so that we can calculate the weight update explicitly. The natural learning rule in this work doesn't rely on human's design, but only governed by physical law. So I cannot give you an explicit expression, but we can still conclude some features. First of all, the conductance of this texture, let's say the horizontal conductance, which will increase for a given voltage. So this is corresponding to the positive feedback process according to the Hopfield's theory. And however, such kind of positive feedback process is not sufficient. Otherwise, the conductance will increase and finally explode, which will never converge. So there's another feature embedded in this system, which is the competition between synapses. When one synapse is strengthened, the other synapses, let's say the vertical synapse, will be weakened. For the simplest square film case, the increase of such horizontal conductance leads to the decrease of vertical conductance. And the competition between the synapses are provided by one, the current conservation, which is guaranteed by this Kirchhoff's law, and two, the zero net magnetization, which is a feature, which a property and feature of such chiral texture stabilized by Jaloshinsky-Murray interaction. And in summary, we demonstrate a hardware version of a 4-node Hopfield network. Weights are encoded in adaptive textures. The network can learn by itself according to physical law, and the learning rule is not designed by human beings. This paper was recently published on PRB as a letter, and I would like to acknowledge discussion with Professor Shunsuke Fukami, Professor Yuan Zhe, Xia Ke, and Dr. Guo Hongwen. And two more slides. So the idea of this work is demonstrated via numerical simulation. So the dynamics of the magnetic system is governed by LLG equation with terms of spin transfer torque. And the current distribution is given by the Ohm's law, given by a specific magnetic configuration. Such a multidisciplinary simulation cannot be easily done via popular software such as OHM and Mumax. So we develop a micromagnetics module based on COMSOL multiphysics so that we can not only perform traditional micromagnetic simulations, but also multidisciplinary simulations such as cavity spintronic system or spin mechanics system, where the spin waves can be coupled with microwaves and elastic waves. And we can also do some other simulation between, such as the interplay between magnetic textures and electric current demonstrated in this work. You can download this module file freely and via this QR code. And I have also uploaded the video examples on this website. So yeah, this is the end of my talk. Thanks for your attention.
Thank you very much. Actually, we have a lot of time left for discussion.
Okay.
Do you have any question or comments? Yes, please. Yeah.
Thank you. So you said in slide 15.
15. Okay.
You described the learning process with 4
Yes.
voltage probes. So my question is whether this learning process depend on the initial configuration of the magnetization.
Yeah. Yes and no. So yes, because it actually depends on how you start. If in the beginning the texture is in the ground state of, let's say, this state, and if we want to train it from this state back to this state, it will take a very long time. And when the network is, let's say, is larger enough, maybe we will not easily train the system from one state to another state since they are very far away in the parameter space. So this is a yes. And a no means that when we apply the electric current, a very strong electric current, and the training will be very robust. So no matter where we begin, and the system will finally move to the memorized pattern, because the training is governed by this spin transfer torque process, which is very robust.
Okay, thank you. So which will be translated yes, yes or no in experimental situations. For example, we try to emulate the same thing in experiments. So would it be yes or no in experiments?
In experiments, I think for this stage, I'm also in collaboration with some experimentalists, and they complain to me that so the situation is yes, because in experiments we cannot apply very large electric current, otherwise the sample will just burn.
Mm-hmm.
Right.
Yeah,
so
okay.
This is an issue. Yes. Yeah. Okay. Thanks for the question.
Thank you.
Any other question? I have a question on this slide. Okay.
Okay.
You were finally you got some let's say conductance between the terminals. Okay.
Yes.
In this case, the distance between terminals are different for example, for the diagonal
right.
terminals. So
yeah.
if you now it's kind of symmetric, but if you have 5 terminals, the distance between them is kind of complex. So in that case, that kind of the Hebbian type learning works to converge to some actual stable state?
Yeah, this is a very good question actually. So yes, so this is a feature. I would not like to say it's a drawback. It's a feature of this system because the physical the spatial information is also included in the physical electrodes. So for this very small network, it works fine. But for a large enough, let's say 100 by 100 electrode arrays, so will it work? The answer is that if the two electrodes, they are separated far away, and then their correlation will be very low. So but however, this will not be a problem because the principle of Hopfield network of such associative memory is to store information into the correlation between neighbor nodes. So the information from neighbor nodes are the most important, and the neighbors from very far away may not be that important. And this is how we memorize patterns as human beings. So sometimes we always focus on the details, but as human being, we can also memorize the global information, right? Yeah, so I think this is a feature. And now I'm working on to scaling up the network to see whether it works.
Okay, so it looks like some similar to our cohonents, the feature map, rather than Hopfield type network. So it's a kind of the mapping of the information of outside into the the structure on your device. So
right,
this is very nice. Yeah, good, very good.
Yeah, thank you. Yeah, thank you.
Good. It's very interesting. The other question I had, you showed some resistible array type figure. It looks like for me, it's very resembled for the horizontal cell in the retinal system in eye. So maybe you can use this for such kind of the process for in the eyes. I think if you use this, yeah,
it's called.
This is just comment. So
yeah,
yeah,
it's very inspiring. Actually, I also have similar ideas, and in my mind, it's so I forgot the English words of this. Yeah. This is how our eyes work.
Yes.
Great. It's called retina, right?
Retina, yes, retinal.
Retina, yes.
Horizontal cell in the retina. Yeah.
Yeah.
Good. Do other people have any other question? Okay. I have one other question. Okay. Please.
No, I have no question.
Okay. I have one other question. Your modeling is actually you express the conductance in a distributed way, but in your model looks like a lumped resistor, I feel. So which actual device is actually distributed resistor, right? So
yes,
it's a little bit different from the neural network model. Actually, it's distributed connections. So do you have any comment on that?
Yeah, no, sorry, because I'm a beginner in this field.
Yeah. Okay, so it's okay. Your Hebbian type learning is working, but if you use another type of learning, maybe it will be a kind of difficulty you have, I think. But I don't know.
Okay. Yeah, regarding to this topic, I have been considering to modify it to some feed-forward neural network, and there will be problem for back propagation.
Yeah.
So for one layer, it's fine, Because for Hopfield network, it's actually a one-layer network.
Right.
But for multi-layer networks, we need to. It's still a question how to train the system through multi. Yeah. I'm looking for something similar to back propagation in this system. Yeah.
That's good. Okay. Thank you very much.
Thank you.
Thank you. Is there any other question? If not, I think
I have one.
Yeah.
I have one
Yeah.
question.
Please.
Okay, and my question is about the repeatability and producibility. If you make that Hopfield pattern samely, let's say 2 or 3, 4 devices, the learning characteristics should be the same, right?
Yes.
And
Actually, this is from simulation. So in simulation, I have run many simulations starting from different initial states. So in all the simulation, it can finally converge to such stable configurations. I cannot say that they are exactly the same every time because this is very complex. But finally, the energy minimum will be the state I feed it to it.
okay.
So this is robust. Yes.
Okay, this will be followed by these questions. If the real device has a little difference in terms of boundary conditions of the pattern at the edge, so this will bring the future difference in terms of learning characteristic. So that is also that should be recognized as a feature. Is it correct?
You mean the effect from boundaries?
If the boundary shape is a little slightly different, the feature boundary of the I would say in the slides you have the circle pattern.
Right. And the boundary actually doesn't affect a lot actually, because when the current flows through this film, there is very little current flowing through according to the close to the boundary, because current only flow through electrodes to electrodes.
Okay.
And,
So if you have a relatively the larger distance between the edge and the node, so it won't be a big problem. Okay.
Yeah.
Interesting. All right. Thank you very much.
Yeah. Thank you.
Thank you very much. We have about 5 minutes left. Do other people have any question? Okay, if not, thank the speaker again, and thank you very much. And I will pass back to the organizer for this session. Thank you very much.
Thank you, Professor Horio. Thanks to all the speakers and all the participants who were patiently listening to the lectures. Thank you very much. See you tomorrow. So I'll pass the mic to Professor Tanaka.
Thank you very much for very active discussions. So we are looking forward to tomorrow presentation discussions. Thank you. See you tomorrow.
See you all. Bye-bye.
See you. Thank you very much. はい。
堀尾先生、ありがとうございました。
いえいえ、明日は授業なんで申し訳ないですけど、はい。失礼します。
Thank you very much.